Thank you all for joining us for the inaugural Texas FIRST Robotics Competition workshop, hosted by FIRST RGV. A little bit about us, and then we will turn it over to our presenters today. FIRST RGV is a nonprofit founded in 2015 that supports the FIRST community in the Rio Grande Valley, which is an area approximately 3 hours long by 2 hours wide, sits next to the border of Mexico. Yes, in Texas, it's easier to measure by driving hours than miles, just because Texas is just large. Since 2015, we have seen explosive growth of teams in our FIRST LEGO League and FIRST Tech Challenge program, but our growth in the FIRST Robotics Competition program is positive, but we are not where we need to be on ensuring access to the more than 250,000 students in the K through 12 space here in the Valley. With our events like this, we are doing our part to create awareness of our efforts and the need for strong sponsors and mentors to help our community. We are proud Texans, and I'm honored to be part of the FIRST in Texas Robotics Territory. Our organization is proud to be hosting this weekend's event. If we have any technical issues, please remain patient. We will get them resolved as quickly as possible. While you're engaging in the chat, asking questions, and saying hi to your neighboring team, or maybe a team across Texas, we ask that you remain on topic and know that this session is being recorded for teams to take advantage of this great information later. We will post this information on the FIRST RGV YouTube channel, and you can access it directly by visiting youtube.firstrgv.org or by searching for FIRST RGV on YouTube. I want to personally thank the FIRST Robotics Competition teams across Texas that have come together this weekend to make this live event possible, and for the hard work of our FIRST senior mentors and AmeriCorps Vistas across Texas that stand ready to help support our teams. On behalf of FIRST RGV, we hope everyone has remained safe during this pandemic, and we are confident that all of the partners across Texas will be getting ready to bring you a robotics season soon. Thank you.
Hi, welcome everybody. I'm Alan Gregory, the head coach for Spectrum 3847. Today I'm going to be talking about FRC prototyping and kind of what that means and how teams use it throughout the season to better their robot and better their season. I think one of the first questions we have to ask when talking about prototyping is kind of what is a prototype? The term gets used a ton in FRC, right? It's one of those things like, oh, you didn't prototype? Well, that's why the system didn't work, and all these like kind of things. But there's so many different definitions of what people think of when they think of prototype that it's actually really hard to communicate well when you talk about, oh, we built a prototype for something, because a lot of people's prototype may be spinning at something with a drill and testing if it kind of, intake a ball at all the way up to building a full robot. So there's a lot of different levels of kind of what are prototype of a different prototypes that teams build and different ways they use them to build a better robot. I think kind of the most important thing about a prototype is it's not the thing you go out and compete with, or at least you don't intend to, right? It's ideally something you built before you build the part of the robot that's going to actually go on your competition robot and see a competition field. Normally your prototype is something you build before that. So some of the different types of prototypes, when I was kind of trying to categorize it for this presentation, when I think of different things that people have called prototypes over the years, one of the things we do for Spectrum at the very beginning of the build season is we'll have kind of concept prototypes where someone has an idea, they think maybe that's how something might work, but they don't really know, right? We don't know if it's going to function that way. We're not trying to necessarily like design something around it. We're just trying to figure out, does this idea work at all? What can we play with to kind of get where we need to be to then actually start working on a design and pulling forward and like learning about that specific design afterwards. And we'll go through these in more detail in a second. An optimization prototype is something that's kind of built to learn a very specific thing about a system. So they can have a lot of adjustability built in, and you can set kind of variables and things. They look very different than what would be on a real robot because you might have a wide range of adjustments and things. And it's kind of like a test fixture or test jig. Single system prototypes start looking more like something that would actually be on a robot, but they're often built faster, they're built quicker. An integrated prototype is going to have multiple systems connected together. And then the full prototype robot is normally like a full functioning robot. It's just not built as well as your competition robot. So for a concept test, a lot of times you're doing things that you're not putting a ton of thought or planning into as much as just trying to get something done so you can learn about the system quickly. Yeah, just trying to get a general feel for the problem. You're not really designing in a ton of adjustment. You're not planning to use this for very long, right? It may be something that gets put together one day, tested for the next day. Maybe a few minor adjustments get made to kind of make sure whether it works or not, especially if it doesn't work the first time, which it most of the time won't. But it's not going to be something that you're really collecting a lot of data for. It's not like a scientific instrument at all. This is our 2013 frisbee launcher as an example of something I would consider like a concept test. There had been some videos of other shooters tested that were all using pretty large wheels. They were using like 6-inch pneumatic tires or 8-inch pneumatic tires to shoot these frisbees. And part of what we had kind of was hoping to be able to design was a smaller shooter to fit in a smaller space on our robot. So we needed to kind of build out a concept test to test whether we could actually launch a frisbee from the distance we needed to into a goal with smaller wheels. So one of our students put this together with basically a couple versaplanetaries and motors, some wood basically, and a little bit of Lexan that was just like scrapped from other projects, right? None of this was cut to precision. None of this is really mounted all that great. There are a few measurements to kind of make sure the frisbee is going to touch the wheel and things like that. But there was no CAD, there was no planning, nothing like that. There's no base for it. I'm literally in this picture just holding it in my hands while a student feeds a frisbee through. And I think the motors are just running at full power. There's no speed control at all. So a lot of these things, there's not a lot of finesse here in the concept test. We're just kind of seeing if it works. The next level up from that is something that's more of like an optimization prototype, where we're trying to test a number of different variables and finding which one of those variables is going to lead to the best results, or at least get us closer to the best results. Depending on what it is, sometimes one of the most common things you're testing with an optimization prototype is something like ball compression. It's very hard to just intuitively know exactly how close your wheels need to be together in a shooter or in an intake or anything like that. How much can you squeeze the ball and pick it up? So often you need to test that, but it would be very annoying if you tested at 6 inches and that was okay, and then you had to build a whole nother version to test at 6.5 inches, to build a whole nother version to test at 7 inches. That would be a really slow process. So some sort of optimization prototype or test fixture, test jig allows you to design in all of those ways to adjust those variables. This example is a 2016 shooter prototype that we built. It was based on a design that Greg Nadell did for 2848 at the time, I believe. This is a while ago, so I think that's all correct. And it allowed us to easily change wheel speed. So we had 2 versaplanetaries mounted on there, so we could even change gear ratios, but we could also change sprocket size up at the top. So those are those chain paths. And there were slots so we can move the motors around to get the chain tension right. So even if we swapped sprockets, we could still get chain tension reasonable for the prototype. And then the hex shafts running through it allowed us to very easily change the wheels. So we could pull the hex shaft out, put a different wheel on. We could put multiple wheels on. We could change the spacing between the wheels. And we could also change the diameter of wheel because we could have a different wheel size. And the way the bolt pattern is set up, you could change the distance between the wheels, I believe on like on 1/4-inch increments going out. So we could have 5-inch compression, 5 1/4, all the way out to however as much as we needed for that test. We ended up not building a horizontal wheeled shooter, but that test fixture kind of allowed us to do some of those testing things and kind of get in the right ballpark if we wanted to end up building that. As we move up, you get to things that are much closer to what they would really be like on the robot. These are like our single system prototypes. This is what on Spectrum we have. We divide up into subsystems that each that we have either a person or a pair of people working to. They're kind of like leading it, managing that whole process, and so they'll manage their single system prototype pretty early. That's one of like the big milestones of the project, is getting to a single system prototype, and seeing how well you can get that to function nicely and what you can do to test it. A lot of the critical geometry is going to be similar to what you would expect to find on the robot. So in some of the other optimization tests, you're building out a pretty wide range, right? You don't really know what's going to be on the robot. Here, ideally, you have already figured out something close using some other test method. So you're building something that you don't think you'll have to change a huge amount, right? Like ideally, maybe the roller's a little tight in your next version, you expand it a little bit, but it's not going to be 2-3 inches off. It's going to be within some small range of adjustments. It's also in a similar way to how you like package it on the robot. So this, the example is our 2019 cargo intake. It definitely looks a little odd here, but we had to build up kind of a geometry out of wood and things. There's a lot of these panels were all replaced by Lexan, and they weren't mounted the same way or anything like that on the competition robot, but largely everything is in the same place. So all the rollers are the same distance apart. They each have their own motor that's able to spin them. So we could get a pretty good idea of what intaking cargo would look like, even though we weren't mounted on an elevator. This whole thing is actually on like a wrist that would tilt, but we built it at the position it would be at for intaking cargo, because we knew that's what we were testing. We were testing the intaking process. We knew we needed to be able to run it against a bumper. So we had one of our old bumpers sitting there acting as the bumper material. So we could see how the ball would compress over and around the bumper. There's some plywood under the bumper to kind of test the height, to get the height right for where the bumper would actually be mounted on the robot. So there are a lot of little details you start adding in to try to get it as real as you can before you actually end up building the real one, or even before you have a real robot to test it on. In this photo, the pneumatic deployment is correct too, because we knew that was going to be part of it. We needed to be able to deploy the intake down on top of a ball. Sometimes we need to be able to bring it up and make sure it held the ball in place. So all of that was built in to the prototype. That was all made out of, this was laser cut wood, but you could do it with a router. You could do it with printout jigs or printed out piece of paper that you tape on and cut to make the same panels. There's all sorts of ways to make the prototypes. Whatever works for your team is fine, but a lot of it is in the details of making sure what you're prototyping is going to be similar to your robot. And we'll go over that a little bit more later as well. Another type of prototype is more of an integrated prototype. So when you're trying to figure out how multiple systems are going to work together, and they don't have to necessarily, not each system could be at kind of different levels of complete. So in this example, our 2018 intake, one of the things we realized was we were building like this big arm that was going to come over and be able to intake on both sides of the robot, and it had to have, and the intake would have to be in like this different angle position. So we were able to build up this very quick chassis. It's just made out of 2x4s. It has some bolted in shafts that we put Omni wheels on, so we could roll it around. We could push the whole thing into the cube to test how the intake worked by actually like kind of mimicking that we were driving it into the cube. And then we could take our hand and we could move the arm. So we could flip the intake over to the other side, see if it worked reverse, see how well it picked up the cube, like how much did it hold the cube. So we could like shake the arm, was the cube going to fall out of the robot? And we could test all of those things. So the intake itself is pretty high fidelity. A lot of those panels ended up being very similar to what we cut at a polycarb for the real one. But the arm and the chassis are all very low fidelity. They don't look much like the robot actually looked. They're kind of the same general shape and size, but we weren't too worried about getting everything right there because that wasn't what we needed to test, right? We needed to test that intake angle and all those things. So that part we did get right as much as we could, and tried to make sure that the intake was going to work the way we wanted it to. And then the kind of the full system, everything is a full prototype robot, which don't always get called that. Sometimes they're people's practice bots, but it kind of, if you just say practice bot, some people also build their practice bot after they build their competition robot, where this one kind of specifically is used for a lot of testing. So this was in 2020, this was one of our first years of basically intending to build a practice bot. It kind of happened mid-season, or building a prototype robot, sorry. We were building along and we realized there were a lot of things we needed to get kind of fully built into the package it was going to be on the robot to be able to test properly. And we needed to do it quickly without waiting on the competition robot, which always takes a little longer because we have to, there's paint. The electrical is always much nicer on the competition robot because we're way more worried about reliability on the competition robot. A lot of the parts take longer because they're made out of more materials that take a little bit longer to machine sometimes. So with the prototype robot, we could get there, like you can see, there's some like masonite on it instead of Lexan. The bumpers don't have fabric. There's a lot of little things missing. And actually, the one bumper on the back actually does have fabric because that's the one that interacts with the balls. So that's part of our testing. So we made sure that one had fabric, but the rest of it doesn't. So a lot of it is just what can you do to get something where you're controlling the aspects that may actually affect the robot, but you can get a mostly fully complete system together that you can test, see what else needs to be tweaked before putting it on the final robot. Had the season continued, this would have became our practice robot. So we had quite a few upgrades to do because we had to turn a lot of things that were made out of like plywood and done really fast and were version 1 into plastic and things so that we could have it a little bit closer to similar to our actual competition robot. But this prototype made our competition robot way better because we could test like the full integrated system and make sure our shooter was doing what we wanted to and things. We could build multiple versions of the hood onto it. We could do a lot of things onto the full prototype robot that we would have been a lot harder to do with just a integrated prototype. Like some of it would have worked, some of it wouldn't. So having it was very useful this year. Okay, so we're gonna go through some of the kind of general concepts now that we kind of have an idea of the different types of prototypes. So I think I may be misquoting, but I believe there's a JVN quote that is something along the lines of, you don't have to prototype everything, just everything you want to work. And that is largely true for a lot of systems, right? I would never want to design up and produce an intake and just take it to competition and assume it worked. Anything that's going to interact with the game piece, anything that's going to interact with a lot of the field, it's going to be very hard to do that. But there definitely are times, and there definitely are times for different teams where it does not make sense to prototype. So if there's a problem that you understand and your team understands very well, and you're confident that your first version and your first version of the final design is going to be sufficient, that whatever it is, you can tweak from there to allow yourself to go without having to like very quickly replace the whole thing, right? That's one of the things that's ideally what Prototype is doing. So you don't have to completely overhaul your actual competition robot, which normally costs a lot more, takes a lot more time, and you can do it out of quicker materials and things. That's why we do a prototype. For things like an elevator, it may not be necessary to build a wooden elevator or something like that, right? As a team, you have to kind of decide, what is this prototype going to really teach you or help you learn or kind of change about your final design? There's so many examples of elevators from teams. There's so many examples of COTS elevators, different ways to power them. There's so many examples and known kind of good implementation practices that necessarily building a prototype may not help you. However, if you're building some new type of elevator type thing, you may want to build a prototype. You may want to see, oh wait, some other thing needs to be adjusted. This is going to change. It's going to iterate a lot. So if you're not planning to have to do a lot of iterations, it may be okay to not build a prototype. There are also some systems where the only real way to do it is to kind of build the full iteration, because the prototypes, you kind of know that testing it won't necessarily work. We had some there. I'm imagining there were some like 2019 climbers that would have been really hard to build a full prototype on, because so many of them were integrated with the elevator and integrated with the intakes, and when they're just too complicated to really just build a prototype until you have kind of everything laid out, where it may be necessary to kind of just go with it and then plan to iterate from there. Another very important reason not to prototype is if you have limited resources, a lot of times it may not be necessary to waste them on prototyping. Right? If you can't get your prototype to a level that's sufficient enough to be useful to you, then it doesn't really help you to prototype, right? Don't just prototype for prototyping's sake. Prototype because it's going to help you build a better robot. So if all you can do is design your final version and get it and then tweak it from there, then do that. If you're building something like an EveryBot inspired robot where they've kind of done some of the prototyping for you, then that's another reason why you can go straight into building your first version and iterating on top of it, since you have a pretty good idea that it's going to work, right? You shouldn't have to rip off the entire EveryBot intake that you just built. If you followed the instructions, you've seen theirs, then you know it works. You already have an idea that it's going to work. The prototype isn't necessary. I kind of already been harping on this a lot through the other slides, but I'm going to make sure we say it again. Before you start prototyping, you absolutely should have an idea of what your goal for the prototype is. We should be very specific about that goal. Our team gets caught in this sometimes where we'll have a student or even myself go, oh, we need to build a prototype of this thing. We're like, what are we actually trying to learn from this thing that we're trying to put together, right? Like, is this thing even close enough to what would be on our final robot, or similar in design enough to be on a final robot that we can actually say, okay, this worked, therefore our final design, the thing that's going to, the first iteration of a robot is going to work too. Sometimes it's not. And so at that point, ideally, if you're asking yourself this and really thinking about it, you can save yourself some time, save yourself some resources, and not build it and kind of come to the problem in a different way, or find a different way to meet the same goal of proving out the concept or proving out the design without building the prototype in the same way you were planning to. It's also very important to know what the goal of the prototype is, because a lot of your design for the prototype and kind of how you build it hinges on what you're trying to learn and what you're trying to get out of it. So having some sort of hypothesis, like, okay, we're building this specifically to figure out what our shooter spacing is, or we're building this specifically to figure out what our intake spacing is and intake geometry. Because there's tons of ways to intake a ball, right? But you have to figure out, okay, this prototype is going to be designed to make sure we can intake multiple balls at once, or that we can intake balls into specific part of our robot, or that we can do it at this speed. There's all sorts of different things you can start listing, right? Some of that is in your strategy discussion that happens at the beginning of the season when you start figuring out what things you want your robot to actually be able to do. Just building an intake prototype is normally not the right answer, right? You need to be building an intake prototype that does what you set out to do and proves what you set it out for it to prove. Kind of along the similar thing of knowing what your actual subsystem and what part of your robot is going to actually, what design requirements and design constraints is it going to actually have to meet, right? There are game rules and robot rules. Your build schedule, like how often do you meet, all those things. You could design this, and you could design in CAD an awesome prototype, but if you don't meet often enough, or don't have the right tools, or don't have the right materials, or it's just too late in the season to do it, there's all sorts of reasons why a prototype may not be useful if they don't meet the constraints you have across both the robot itself, but also your team. Right? There could be an awesome climbing system, but it ends up weighing too much. So then that prototype wasn't useful because you weren't looking at the weight constraint for how much weight you actually have to be able to put this climber in place. Motor and pneumatic allocations are a similar way. If you don't have enough motors left over on the robot for your system, it's not going to work out, or you have to like figure out, or you may have to change another part of your robot to change some of these constraints, right? Maybe your prototype can't get down to weight, or can't get down to the packaging constraints. Then you may have to move something else or change something else to allow it to work. Okay. This is probably one of the ones that I think a lot of, not necessarily a lot of teams, but a lot of people miss with the idea of it being attached to prototyping. Because a lot of people do this type of thing kind of early in the season. Well, they definitely will look at a different robot, right? It's a shooting game in 2020 and 2021. So a lot of people did look at 2016 robots or 2012 robots and we kind of saw these different examples, but they may not have seen and done a lot of research into the specific prototypes that were built from those years, right? How did they go about actually doing the testing, not necessarily just what their final product looked like? There are a lot of examples of those types of things in old Chief Delphi threads, and a lot of teams will talk about them in some of their videos. So in watching some of their final robots also helps. So things like the Behind the Bumper series that Fun does, those have a lot of detailed looks into different robots. So you can see kind of different designs. Tons of teams post their CAD models. Recently we collected a lot of them in a Google Sheet. So if you go to cadcollection.spectrumtheatre7.org, you can see, I think it's like 800 something robot CAD files right now. So you can dig through a lot of old robots and see how they build their robots. So you can get a lot of information without actually having to build a prototype first, right? Or even do a concept test, right? If you can find somebody else who's proven out the thing you're trying to learn for you, you don't have to do the work. And then your work and your energy can be put into improving it and iterating it and making your final design better. A lot of published examples, things like the Open Alliance, which Spectrum is a part of, and a lot of other great teams where we're putting out kind of a lot of what we're prototyping each season, our final designs, all sorts of resources for you. So where you don't have to, like I said, you may not have the time, energy, resources, whatever it is. You can see a lot of different examples of things that have worked and a lot of things that haven't worked as well. Everybot is an awesome example of robot archetype to play with. They build a pretty good one every year, and a lot of teams should definitely look at that as their base robot. Robot in 3 days teams. YouTube has a ton of examples that people put out, especially at the beginning of the season. One of the things a member of our team started doing was basically daily going onto YouTube, searching the game title, so like 2020 Infinite Recharge or Infinite Recharge, and sorting by upload date and just seeing what teams were posting, because teams have vlogs and all sorts of things where they're posting their prototypes and they're posting their experiences with the game. So you can be collecting and kind of curating all sorts of information and ideas from teams around the world. Another important aspect of it is talking to other teams. A lot of teams don't realize how often other teams are discussing their ideas and talking about what they're doing in their shops, right? There are very few FRC teams who are in this alone and are just, we only talk to ourselves, we don't do anything, or the very few teams who do that and are successful. Most of us have either mentors who are talking to each other, we have team members who are talking to each other, either sending videos and pictures or just discussing ideas and things. Be like, hey, we had this shooter concept, it was working all right, but we think the double wheeled one is better. Like, there's all sorts of little conversations you can have that inform your testing and your prototyping, again, without you having to test every single idea, or also come up with every single idea. There are a lot of good ideas, there are a lot of bad ideas. Figuring out which is which isn't something you're going to be able to do for every single idea in a game in the season. Okay. The concept of prototype fidelity is basically making the prototypes as close to what they'll be on the real field and what you'll see in real competition as needed for that specific prototype, right? If you're prototyping an intake and it's going to be intaking a ball over your bumper, most of the time you do your testing, you really want to have a bumper that's fully wrapped in whatever bumper fabric you use as your team and you're planning to use that season. Ideally, you want to have it on a reasonable carpet that's close to the field carpet, right? You don't want to test your intake on slick tile or something else where the ball is going to have a different characteristic, right? It may be very hard to intake a ball when you're doing it on freshly polished school hallway, but it might be very easy to do it on the FRC field. Same with like goal heights, like when you're testing for shooting and things, you want to make sure you're testing a shot that's going to actually be on the real field, right? I've seen teams try to shoot, they were like shooting balls into trash cans or something, but that's very not different, or it's very different from the goal that you're shooting on in the 2020 game. That's not really necessarily useful to be able to do that very well, because when you put it on the field, that's not a task you have to do. Similarly, you want to actually like mount things to either a robot or either you can push or drive it around. So if you have an intake, it doesn't always help to just roll the ball at the intake. Rarely in a match are balls just going to come nicely rolling into your intake. Most of the time, your robot's going to drive over and intake them. So you want to mimic that action as much as you can. Kind of a lot of our initial tests, we'll roll the balls in and see how it works. But then at some point, we try to get it onto a moving chassis to where either we can drive it in or just push it around and move it in to really simulate the field conditions as much as we can. Another thing is integration with other robot parts. Like I said, if in our 2018 example, our arm and our intake, we definitely had to make sure we were intaking kind of at the right angle and that the arm would be able to lift it up and still hold the cube and everything. Balls being fed into the shooter is a big one. How much that affects like shooter accuracy and shooter consistency is a big deal if you don't have your balls being fed reasonably into the shooter. If you're hand feeding them and you're pushing them in with your hand instead of just like letting the shooter take it or having your feeder take it, those can all affect the validity of your results of your testing. Okay, so once you actually decide, okay, I've done all this research, kind of know what's going to affect some of my robot elements, then you have to start thinking about what are you actually trying to test and what are the variables for that system. So one of those big things that we're trying to look at whenever we're designing systems and things is what are the aspects of the design that are really going to affect performance. So a lot of those things are things we've already mentioned. That's like shooter compression. There's also thinking about shooter prototypes. We had different hood materials. So we had foam or we had slick like PTFE sheet. We had different wheels. We had different wheel spacing. We had different motor speeds. We had like an accelerator wheel. We had all these different things that could affect our shooter performance this year that we had to kind of figure out how we wanted to go about testing them and what systems were relatively easy to basically set and say, okay, this is going to be kind of how it is, and we're going to adjust from there. And how do we make, and what things we wanted to really be able to like test and tweak and change out if we just weren't sure if something was working or not. Ideally, your prototype should inform your final design, right? You don't want to build a prototype that uses a foamed back shooter hood the entire time. And then when you go to the final design, you switch your shooter hood to plastic or something else that's different, right? You want to be using as close to the final robot parts in every way that you can, or in every way that's going to affect the shooter, or the prototype, sorry. A good example of this is this year, our 2020 shooter prototype, which I think I have a photo of later. We ended up figuring out that because we were building the shooter hood, the prototype of it out of laser cut plywood and some like spacers, it was actually flexing a whole lot more than our final iteration did. So we went and built the final iterations. All of our shots were unbelievably low because we just didn't notice the flex in the shooter while we were testing this year. It's one of those things that we definitely should have been paying attention to, and it just kind of slipped. And we were like, oh, the shooter's working great. We're making all these shots. This is awesome. We'll build the final version. We'll build like the next version. And it just was not happening. We were literally like shooting just straight well below the goal, just like almost in a straight line when we put that together. So yeah, you really want to notice, do whatever the differences in the prototype are compared to the final version, is that going to affect its performance and how? Flex is a big one. That's one that bit us this year that we had to do a lot of tweaking on our hood pretty late in the season to get right. There's a lot of less precise alignment and things if you're not putting things together as accurately and as well as you would on your final version. A lot of little things can be tweaked on a prototype that aren't going to transfer to the final version, and that may cause you to not get it right. In general, for your prototype, you're finding good, not perfect. Because there are going to be differences, like I said, that there's going to be flex, you're building things not of the same materials all the time. If there is something that needs to be kind of perfect on your robot, you probably need to design some of that adjustability into your robot. So if you can design it to where you can change your shooter speed because you have different settings in the control system, or you can change your hood angle in some way by dialing something in. You can change like hard stops and things to change exactly where your intake falls. There's all sorts of little things you can do to kind of tweak your final version if there's differences between your prototype and your intake, or in your final version. But you definitely have to think about those during the design process of your final version to get it right, to know, okay, maybe the prototype isn't quite right. We'll be able to tweak this a little bit in this range of values, but the prototype's close to right. Another very important thing, and I feel like this is also one that not a lot of teams do all that well. We also, even with all the documentation we do, we don't do it as well as we should. Documenting the prototyping process, making sure you have good photos, videos, and a lot of notes from the time you're actually doing the testing and everything, along with those measurements, helps a lot, especially later in the season. We're like, well, this was working, sometime during week 2, we had this working. Why is it not working now? And if none of us can go back in time. So all we can really do is take good documentation so that we have that reasoning, and ideally it can inform our design and it can help us later on in the season. Some of the things that Spectrum does during our prototyping process and kind of our entire development process, we have a big design slide deck each season, so where all of our members can go in and add slides and kind of take notes of what we're doing, different ideas they have, all sorts of different concepts get put in there so that it's shared amongst the team. We have a design sheet that's set up that way too, so we can document some of our testing results. We can document some of the spacing things. We also take a ton of video and photos that we have in a gallery that gets shared among the team as well. So a lot of that gets documented, but we definitely don't do it as well as we should for certain processes, and we can definitely make that a little bit better as well. Feedback is very important. There are a lot of people who have been doing FRC and FRC robot development for a very long time. And some of that is you basically build up intuition after you do it for a while. And so being able to have some idea if something is on the right track isn't always easy for teams, but it's very easy for people who've been doing it a long time and have designed successful robots before, or been a part of designing and running successful robot teams. So being able to put your idea to some teams you trust publicly works too, right? Chief Delphi, Discord, whatever, and getting some feedback back and being like, hey, yeah, that design makes sense. Or yeah, we think that's a really cool concept that might work. But you also might get feedback back, hey, maybe if you try this, it might work even better. Or, oh, we tried that, but this is the problem with that same concept that we ran into. Have you seen that same result? Or did you find a way to solve that? And we get that a lot, since we, as Spectrum, we publish basically everything. We'll get notes and stuff sent to us by different teams, by different mentors, kind of commenting on our things that we use to better our design because we're able to get that feedback. So especially if you're a young team or you don't have people who have been doing FRC for very long, there's no reason to really keep your designs and ideas secret. It doesn't benefit you. You'll get so much out of it by asking for feedback from other people that you trust in your community, either local or online or whatever you can do, to just get kind of a double check. Because a lot of times if you're kind of in it and you really want something to work, you may not see the glaring errors that are popping up in your prototype. We're like, oh, that's working because you didn't do so and so, right? Maybe it's only working because you don't have it on a movable chassis, or you're not integrating it with your shooter yet or something. But it's very useful to get that outside feedback and get a second set of eyes on whatever you're thinking about doing. Okay. With the last little bit of time we have, we're going to talk about some of the tools and parts that Spectrum uses and that other teams use to kind of make the prototyping process easier. One of the things that we have, I couldn't find a photo of ours, but we use motor testers. We call them flight sticks sometimes. I'm not even sure where that name came from. I've heard them also called phasers, which is probably what we're going to try to get Spectrum to start calling them. And basically, they're modified drills that let you power a FRC motor really quickly. Ours are just our power drills that we use on the team are 12-volt drills. We've broken the chuck on a couple of them, so we'll take the motor and gearbox out of the drill. I'll basically just add wires to it that have Anderson connectors at the end, the Anderson power poles that we use on all of our motors. So then we can just plug in the motor, pull the trigger on the drill, and now our motor spins. So instead of having to get out a whole control system, a Robo-Rio, and kind of plugging in a laptop and all of those things to just test a single little system, we can do it with just one of those drills really fast. And those are just like hang out in our drill box. We have them all the time. It also helps if we just want to test something even on the robot, you can unplug it from the main robot and just test the intake really fast. Those types of things are very handy. We also have a bigger board. This photo, I believe, is from Triple Helix, where they have a main breaker, like a 120 amp going to a speed controller. We have a board that I also couldn't find a photo of that has one of the old power distribution panels on it, or power distribution boards, with a couple speed controllers and a PWM tester. They're designed for like a servo tester or any of those, and they'll generate the signal for the motor controller to allow you to change the speed. So we use that a lot for shooter testing. So if we just need to be able to kind of lower or speed up multiple motors attached to a shooter, we'll plug that in, and it has 3 speed controllers on it. We can just turn a dial and set our speed pretty easily. And most of it's all used parts plus the $10 servo tester or whatever it is, allowed us to build that up, and we use it basically every season for something. Another one is a pneumatics test panel. So having some way to test pneumatics functions. So if you are building and prototyping an intake that's going to fold down over your bumper or something like that, you want to be able to quickly have a solenoid that you can control back and forth and push air down or let air up, right? Because if you just build a intake that in an actual match is going to come down with air and be held down with pneumatics, but instead you build it completely rigidly, now that joint that would be moving up and down can't at all. So it's going to intake differently than if it actually had the same pressure pneumatics pushing it down over a bumper like it would be on the real robot. So again, you want to get that fidelity right. So one of the ways to do that is to use the pneumatics there and kind of test the whole mechanism. A lot of the solenoids will have buttons you can just press, so you don't have to have them set up to anything with electricity. You don't have to have PCM or anything. You can just get the compressor running, get it charged to a state that's reasonable, push the button, and the pneumatic will move in and out. We'll often also use an old robot, even like last year's competition robot. We know it's working well. We'll unplug, we'll get an air line from it, get a solenoid, and plumb it that way. So we'll have last year's competition robot running up on blocks somewhere. We'll turn it on, and we can test just using that as the air line. You could also even test with a non-FRC setup. So we have a little portable battery-powered compressor. I think it's DeWalt, that we'll use for testing pneumatics sometimes now too. So however you can get pressurized air in a safe, reasonable, regulated way, you can test and you can test your prototypes that way as well. Spare robot chassis are really useful for being able to test intakes moving back and forth. We've used them to test like different climbing or buddy climbing mechanisms, where we've strapped like weights to them to get them heavy enough and seen if we can get balanced buddy climbs and that type of thing in a couple of games. So those are useful to have on hand. So even if you've ripped kind of a lot of the electronics off of Pastor's robot to move on to next year, you can keep the frame and some of it around. Even if you take gearboxes off, if it has wheels, you can push it around and it can still help you out. Okay. A couple of the more recent tools that have been developed, one of which that we'd started working on 2 years ago, I want to say it was in the fall of 2018, is Spectrum Protopipe. So I'm not going to go into all the details, but if you go to protopipe.spectrum347.org, you can see the full document and it explains it. It has all the downloadable files, so you can 3D print the connectors. But basically what it is a system of 3D printed connectors that allow you to connect to PVC pipes with either wood screws or clamps. And you can very quickly build up different prototype concepts and different concept tests, or tests for different variables and things too. So in the video down here in the corner, our students actually modeled kind of that same frisbee shooter that we showed from 2013, but we did it later so we could see what it looks like. So in this setup, instead of having it just be wood screwed into place, so it was a lot harder to change, here we basically have the wheels kind of clamped. We can slide them along these rails. So if we wanted to change the distance between these two wheels, we could. This 2x4 back here is actually on rails as well, so we could slide it. So if we want to change the compression, so you could do a lot of different changing on the shooter without having to build a new one. You could kind of start learning more about the problem here. Another example, so this one was built up to mimic the 2010 game, FRC Breakaway, where you had to have a soccer ball kind of in your robot, but you weren't allowed to actually bring it in your robot. You just had to like roll it, or you had to have it in the front of your robot. So we had two different rollers here. They were just powered by drills. So we didn't even have FRC motors on these ones. And these pipes are just spinning in those connectors. So we could get kind of a concept test built up relatively quickly. We had all the parts ready. We printed we have a big bin of the connectors printed. They don't cost very much. They're just printed out of PLA. And so we can get kind of this test fixture set up pretty quickly, or we can do some of the adjustments on it. So you can kind of like slide these different bars into different dimensions. You can slide them to different heights, and you can start figuring out the problem a little bit through this. Then we might need to build something a little bit more robust to figure out the exact variables everywhere. And then we would get into our first iteration of kind of our system prototype as well. Another very cool 3D printed project called Height Blocks from 5254. They have a mentor, Max, who helped design these. We used them this year for shooter concept. So we needed a prototype to let us spin up multiple different wheels and kind of get everything running. To kind of get everything actually spinning up to velocity and everything. And this way we had the height blocks have kind of better bearing setups and can be a little bit more rigid on the 1x1 aluminum extrusion. So again, a lot of the prototyping stuff doesn't have to be expensive. So we had 2x4 frame that we built up, just kind of 1x1 extrusion. There are some clamp pieces. All of this was being controlled by a past kind of test chassis that we had, because we needed to have brushless motors. So there was actually some code involved with this prototype because we wanted to get good wheel speeds. So we were doing velocity control on these wheels during our shooter testing, even just kind of this initial testing, because we wanted to make sure that the inconsistencies weren't from the wheel speed, but were actually from whatever our setup was. So we wanted to make sure we were being able to test and tweak our setup and figure out a ball distance and how the balls were shooting and everything else through this setup. And there's definitely more. This was not the best prototype. We could have done a lot more to make this better. And we did. This is one of the earliest versions of this. I think we added quite a bit of stiffening and changed the back and changed a lot as we were developing this. Kind of an example prototyping material. Again, you don't have to have finding a system that works for your team is a lot of based on what tools you have, what material and things you have available to you. This kind of example over here is actually one of our initial 2020 shooter prototypes. This was the shooter off of our 2017 robot that we like kind of hacked up and got to a state where we could power the feed rollers and we could power the main drum. And we actually ended up changing them a little bit, because we ended up with like these plywood mounts out here. So we had to change how they were mounted to get them away from some other part of the ball, I think. And then we added some sticks of aluminum and clamped them to this cube of 2x4. So the setup doesn't have to be super precise necessarily to kind of get an idea of what we're trying to learn. Because all this test was doing was seeing how the balls kind of flew in the air. Something I want to say we had this up and running early in the first week. I'm pretty sure we had this going, because we just wanted to know, okay, how do these balls interact with shooters? What can we do with kind of angle and velocity, and how far do they fly? we hadn't really played with those specific balls yet. So we knew that this wasn't going to be what our actual competition shooter looked like, but it was good enough for the initial tests, and we could get it done faster than building up anything else. Oh, this actually does have our electrical panel in the background here too. So there's a spot for a battery, one of the old PDPs, and there's some speed controllers and a little servo tester in the back. Another very useful thing is having planetary gearboxes around or some other way to get an FRC motor quickly to a hex shaft. We use versaplanetaries for most of our prototyping because we can easily swap to different gear ratios, swap different motors. But recently we haven't been using them very often on our final robots, but almost all of our prototypes end up getting powered through a versaplanetary just because of how easy it is to change things. Clamps are super useful, so you can get things clamped together when you don't necessarily have the best fastener for them, and you just need them to stay rigid for a little bit. Lots of sources for parts and material and stuff to use for prototyping, since it doesn't have to go through an entire competition season. A lot of the wood we'll use is this really cheap 5mm underlayment that I think Home Depot sells. It's like $13 for a 4x8 sheet or something, and we'll cut out all sorts of stuff out of that. It snaps pretty easily, but it normally lasts for the life of the prototype. Okay, some last tips before we take a few questions. Slow motion video can be very useful, and a lot of teams have had really good success with it, especially if we're getting some very specific details right in a lot of your tuning. You probably aren't going to use slow motion video on some of your like initial concept tests, but as you're actually tweaking in some of your subsystems, especially like shooters, getting 120 frames per second, there's cameras that can do 960 frames per second. You can really see a lot of details that you would miss in real time. So you can see kind of vibration and shake, flexing of different parts. There's a lot of little details you can see in slow motion that you wouldn't be able to see in when you're just watching it or watching the video. Another really cool thing that teams have done, Spectrum hasn't done this specifically yet, is to use scale models to be able to prototype faster and use less materials. So one of the best examples I know of is 125, the Neutrons, using golf balls in 2017 instead of the fuel, the pickleballs or whatever those were. So instead of a 5-inch ball, you have a 1-inch ball or something along that size. And you can scale everything down to that same scale factor, right? So if you have a 1-inch ball, you make everything 1/5 the scale. So they were able to test their whole feeder concept and kind of 3D print all sorts of versions of it much quicker than if they had to build a full FRC scale version of their system. Okay, so I think that's my last slide. Do we have any questions?
We do not have any questions in the chat, but I've got a couple questions for you, Alan, if you don't
Sure.
mind. When you mentioned slow motion video, I think that's really cool. But do you have any specific hardware that you would recommend using? Do you have a camera that you like or anything?
So yeah, so this year, in the past, we've actually just used some of our students have iPads assigned by the school, and we've actually just used their iPads for it, and then we've been able to do some of it. To go to 960, we actually just bought a Sony ZV-1, which is a relatively cheap video camera. I think it's like $750, $800. It's not like super expensive or high end or anything, but it'll do short bursts 960 FPS. We haven't got to use it in any testing yet, but it seems to work well enough from the little bit I've done. I think there's a couple other Sony camcorders that can do it as well.
Okay, that's cool. And when you're talking about doing your prototyping, do you have any special software you recommend or use to prototype?
No, so most of our prototype stuff, a lot of it is done. A lot of the concept tests are going to be done in just by kind of whiteboard sketches and figuring out what we need to get built. As we move up, then it's whatever CAD package a team uses. So most of our stuff in the past has all been done through SolidWorks. We're kind of a hybrid team now, Onshape and SolidWorks. We're kind of in the middle. It's going to be a weird couple of years as we figure out which one we're going to stick with.
Yeah.
So
Well,
Alan,
go ahead, Mike.
since you brought that up, I have a question because it's come up in some of the other sessions. We had someone actually ask us about doing a workshop on shape because apparently this person felt there was a lot of advantages for teams using that because it wasn't as computer intensive as
Mhm.
SolidWorks and some of the other things. I just wondered about your opinion on that.
Yeah. So, and it's kind of why we're in this hybrid model at the moment. So part of it is so reasons why SolidWorks is useful is one, we've been using SolidWorks since 2012. So for us, there's a lot of institutional memory, right? We have a lot of systems in place. We have a lot of old CAD. So there is some effort into switching the entire team over. We also have several students who are already proficient in SolidWorks. We've done SolidWorks training, right? So most of our upperclassmen already know the system. The other reason for us specifically is one of our sponsors, we have a sponsor who laser cuts parts for us, takes the native SolidWorks files, right? So they do SolidWorks as their main CAD package. We send them the actual SolidWorks files and they open them in SolidWorks there as well. So if we switch to Onshape, we'd have to do a little bit of work and kind of converting some stuff for us anyway. Like we'd have to do the work before we send it to them. So those are kind of reasons to stay on SolidWorks. For the reasons to stay in Onshape, for FRC teams specifically, it is very useful to be able to have a distributed system where not every one of your students does have to install SolidWorks, right? It's a relatively big file. It's pretty processor intensive. Onshape, for the most part, a lot of the things are done on their servers because it's all online. You can be working and looking at the CAD through an iPad, through a Chromebook, kind of whatever you need. You can still run it in Onshape, which is very, very nice. So a lot of actually for this coming fall, as we're doing new student training, we're training all of our new students on Onshape and some of our old students will follow along as well. But we're doing our advanced training still in SolidWorks. That's so much of what our kind of initial or actual robot CAD right now is still done in SolidWorks.
And what is your opinion, or do you know, or have you used what is it, 60? That's another one I've heard mentioned.
Yeah. So yeah, all the CAD packages, most of them allow you to do the same things. It's just a matter of how proficient you are and how fast, and some of them will be faster at some things than others or better at some things than others. For most FRC teams, whatever one they know better, whatever one they can use on their equipment is more than adequate. Like if people were going to start from scratch and we're just asking me which one today, it'd probably be Onshape. There's a lot of tools built in now that a lot of different FRC people in the community have built up that allow you to make it very simple to do a lot of FRC tasks that used to take a while in SolidWorks. But there are still some things that are annoying about it too in the robot design process. It's not perfect. But yeah, Inventor, Fusion, if you have for some reason one of the other, there's a lot of different CAD packages that exist, right? But most of them all do 3D modeling in a somewhat similar way.
Okay. Thank you.
No problem.
All right, Alan, that was a lot of great information. And I just have one last question. And you may not be able to answer this because you've got so much history there, but looking at your presentation, I saw a lot of just common household parts that y'all would use for prototyping. And my question really is for a rookie team to go into the prototyping business, which we know they need to do that, is there a guesstimation on a start budget?
So a lot of that depends on what they're doing as a rookie team, right? So a lot of depends on what their skill level coming in at is as a rookie team, because there's so many different abilities as rookies, right? You have someone who's been in FRC before. Have your students been doing FTC for a long time and they're pretty confident going in, right? They've done CAD training. If you're brand new and nobody on the team has ever touched a robot before, they probably shouldn't be doing prototyping at all. It's not going to be that helpful because they don't even understand what problems they're trying to solve yet. Most
point.
of those teams should be building the everybot. like largely, right? The Everybot or some version of it or some other type of kind of known good concept, right? They should absolutely be using the Kitbot drivetrain. Way more teams should be using the Kitbot drivetrain, right? Prototyping drivetrains mid-season is, I should have had a slide for that. Don't prototype drivetrains mid-season, even though I'm almost certain we probably have at some point. But in general, the best advice is not to do that, right? Have an idea of what your drivetrain is. Build them in the fall if you want to build something cool, swerve, whatever. But if you don't have an idea what your drivetrain is, use the Kitbot. It's awesome. The Andy Mark AM1 for you 4 now is an excellent drivetrain. It works. And then from there, ideally, most young and rookie teams should be using quantities, because you really want to get that experience and understanding of what it's going to actually take to build an FRC robot and do well with it, right? It's so easy to think in your head, oh, we just have to put a ball in a hole. There's all sorts of things that can do that, but it's so much more complicated when there are 5 other 140-pound things running into you at the same time. And just the inconsistencies of the field and the objects, like there's so much to learn and take in, that if you get something that's kind of known and have a good experience with it, take it, tweak it, learn how it works, and then your next season start building on that experience. That's by far the best way to be successful.
All right. Well, that sounds good. Well, Alan, we appreciate your time. We've taken an hour of your Sunday, and we really do appreciate it. This closes out our workshop. I'd like to thank Mike Henry, Daniel Wood, and the Vistas from the Rio Grande Valley for helping put this thing together, and of course all of our teams across Texas in the FRC program for coming together and collaborating on this. And we have a tentative date for October 3rd for a follow-up workshop, which will talk about some more of the non-technical stuff associated with FRC, and we invite all of our teams and coaches and students and everything else to come back and join us for that. But for now, we'll close it out, and we'll see you soon.
This concludes
All right,
this session.
Alan,
If
we're
you're
clear
watching
on
us
the
live,
video
please
and
take
audio.
the time
Thank
to
you.
go back to
You're
YouTube
awesome.
and pick up our next session, or you can always visit our live page at firstrgv.me/live and pick up the next session there. We appreciate you watching and participating in today's session.